everyone, let's talk about the way pressure works to create wind and the way wind flows on a rotating Earth. So first of all, we'll start out with talking about what wind would do on a non-rotating Earth, and then we'll add in the Coriolis force. So first of all, we've got high pressure like this. This is the side view. We have descending air. So if you can imagine that descending air is sort of pushing on the surface, and that creates high pressure. And so then the air would be moving out from that. So from the side, we'd see air descending and then diverging is the word for this. Viewed from the top, so this is side view. And I encourage you to follow along in your notebooks here as well. From a top view, what we would see is a high pressure on the surface in the middle. And now this is on a non-rotating Earth. We would have that wind moving out in every direction away from the high, like so. And then a low pressure system, again from the side first, we would see air converging and rising. So there goes that air up, sort of pulling away from, and that's bringing more wind in from the side there. That's the wind we would feel. And then from the top view, again, we'd have a low pressure on the surface, and the wind would be moving in to the low pressure and then going up, right? So that's on a non-rotating Earth, descending, diverging air. On a high pressure, here it's diverging as well, but it's not doing anything besides just moving away from that center. And then converging, ascending air in the low pressure system. However, as you know, the Earth rotates, and we have to think about the Coriolis force. So first, let's talk about the Coriolis force with respect to the hemispheres we're talking about. So some people say Coriolis effect, not force, because Coriolis effect is a little bit more accurate in describing it because it's an apparent deflection. There's not actually a source of force. It's just the conservation of angular momentum between different places on Earth. If you're a physics major, then you will appreciate that note I just made. If you're not, it doesn't matter. You can call it Coriolis force or Coriolis effect. In the northern hemisphere, wind that would move straight ahead is deflected to its right because of that Coriolis force. And it doesn't matter which way the wind is going, north or south, east or west, it's always to the right of the apparent direction of the wind. So if the wind is going here, it's going to take a right turn. If the wind was going to go this way, oh, sorry, let me look at the dotted line. If the wind would have gone this way, it instead goes to its right. So you can see here, this is taking a right turn, this is taking a right turn, this is taking a right turn. In the southern hemisphere, the Coriolis effect is reversed. Wind that would move in this direction is instead deflected to the left. Wind that would move in this direction is instead deflected to its left. Wind that would move in this direction is instead deflected to its left. So because of this, then we have to go back to our top views of the high pressure and low pressure and model that again. So let's go take a look at the phenomenon of the low pressure and high pressure at the surface with the Coriolis effect included. So we've got, this is going to be northern hemisphere. That's not New Hampshire, that's northern hemisphere. In the northern hemisphere, we would have a high pressure zone here on the surface. This is the top view. Excuse my poor writing here. There's a high pressure, and remember the air is descending and diverging, so it would be going out, but instead of going straight out, it goes out and then it takes a right in the northern hemisphere. And so we observe that the air moves outward, but in a spiral outward from that high, like that. The low pressure, the wind would be moving into the low, but instead, again, in the northern hemisphere, it's diverted to its right. And so the effect is to have the wind not go straight in, but go in a diagonal like this. So the easy way to tell low pressure and high pressure systems from their rotation is in the northern hemisphere, the rotation is clockwise out of a high pressure system. In the northern hemisphere, the rotation is counterclockwise into a low pressure system. Notice this is still diverging. The air is moving from the high outwards. Here it's still converging. The air is moving into the low, but instead of being straight in or straight out, it's curving because of the Coriolis effect. Now remember that in the southern hemisphere, those turns are reversed. So let's change it now to the southern hemisphere. And we need to come back in here and do this the other way around, because in the south, the Coriolis force works the opposite direction. Keep my low there, keep my high here. Again, we have diverging air, but in the southern hemisphere, the air would go straight out, but instead it turns to its left. Like that. So it would be moving into the low, but in the southern hemisphere, it's diverted to its left. So we can sort of draw that like this. And I can keep drawing a few of these around here to make it clear. So what we observe here is in the southern hemisphere, the high is featuring diverging air that is moving in a counterclockwise motion, whereas a low is converging air going in a, and this is, I didn't draw this quite as pretty as I could have, but that's okay. It's my first shot at it here, in a clockwise motion. So opposite the directions of rotation around highs and lows in the northern hemisphere. Hope that makes sense, and you'll get to apply it when we come to the idea of a mid-latitude cyclone, as well as tropical depressions and tropical cyclones.